A review on machine learning. Spatio-temporal data mining, issues, tasks, and applications. Abstract. Spatio-temporal data generally involves the state of an object, an occurrence, or a spatial location over a period. In many application areas, such as traffic control, climate monitoring, and weather prediction, a significant amount of spatio-temporal data can be found. These datasets could be gathered in various formats, at different locations at different points of time. Because of the complex nature of spatio-temporal objects and their relationship in both spatial and temporal dimensions, this raises many difficulties in the representation, ollection, interpretation, and mining of such datasets. Sometimes, spatio-temporal datasets are very broad and hard to interpret and view. In this paper we propose several data mining tasks such as association rules, classification clusters that are analyzed and tested to discover information from spatio-temporal datasets. System functional criteria are addressed for certain kinds of information discovery. Finally, applications are presented for spatio-temporal data mining. Keywords: data mining, temporal data mining, spatial data mining, spatio-temporal data mining. 1. Introduction. Naturally, the data mining progress has led to the discovery of application domains within which data mining can be used. As many of these domains have an inherently temporal or spatial context, to correctly interpret the data obtained, the time and/or space dimension must be taken into account in the mining process. Variable energy resources. The ambitious Renewable Portfolio Standards, RPSs, have been mandated by many countries in the world and many states in the United States. Wind energy itself is projected to rise among various renewable energy resources to provide between 15 to 25% of the world's electricity by 2050. According to another report, since 2000, the world's total capacity for wind power has doubled every 3 years, reaching an installed capacity of 197 GW in 2010 and 369 GW in 2014, CEC, 2013, IEA, 201.3. However, the random nature of the wind makes it difficult to hit the required power balance for its integration into the grid. Accurate forecasts promote the use of ancillary residential sources such as frequency control and load following to compensate for such imbalances. How ETAL, 2013, Sanandaji et al., 2014. With the growing availability and knowledge of huge numbers of geographical and spatio-temporal datasets in many significant application domains, such as meteorology, all types of weather info, moving storms, tornadoes, high-pressure area developments, movement of precipitation zones, freezing level shifts, droughts. Biology, movements of animals, mating activity, relocation and extinction of species. Crop sciences, harvesting, improvements in soil quality, control of land use, seasonal grasshopper infestation. Forestry, forest growth, forest fires, patterns of hydrology, creation of canopies, tree cutting planning, tea replanting planning. Medicine, progression of cancer in patients, tracking advances in embryology. Geophysics, history of earthquakes, volcanic activity, and forecasting. Ecology, causal correlations in environmental changes, monitoring of instances of emissions. Transportation, traffic monitoring, regulation, VI. Clean movement tracking, traffic planning, navigation of vehicles, fuel-efficient routes. 2 issues and challenges list below are general issues and challenges in the representation, collection, analysis, and mining of spatio-temporal data. 1. The fundamental question for spatio-temporal data handling, analysis, and mining is the design and creation of stable spatio-temporal representation and data structures. 2. The specific characteristics of spatio-temporal datasets are that they bear geometric and temporal computations that involve distance and topological knowledge. 3. Knowledge is carried by spatial and temporal relationships such as distance, topology, direction, before and after. In spatio-temporal data analysis and mining, they must be considered. 4. There are implicitly defined spatial and temporal relations. In a database, they are not encoded directly. It is important to extract these relationships from data until the actual mining phase begins. There is a trade-off between processing them and computing them on the fly as and when they are required. 5. Scale effects in space and time are a difficult problem in the study and mining of spatio-temporal data. Scale may have a direct effect on the type and strength of spatio-temporal relationships that can be contained in datasets in terms of spatial resolution or temporal granularity. 6. The unique aspect of spatio-temporal datasets needs major modifications to data mining techniques so that the rich spatial and temporal relationships and patterns embedded in the datasets can be exploited. 7. Neighboring pattern attributes can have a huge effect on a pattern and should be considered. For example, spatio-temporal events such as hurricanes can hang the pattern of traffic jams. 8. Many qualitative reasoning rules on spatial and temporal data, e.g. transitive property, provide a valuable source of independent domain information that should be considered when producing patterns. How rules are articulated and how they can be combined with the process of spatio-temporal reasoning is a challenge. 9. Visualization of spatio-temporal trends and phenomena, scalability of methods of data mining, representation of data structures and effective indexation of spatio-temporal datasets are also difficult problems. 10. Another challenge is the development of appropriate methods for visualizing spatio-temporal information and interact-ion facilities to provide an insight into the underlying phenomena described by knowledge. This includes incorporating the outcomes of spatio-temporal data mining into a mechanism that interprets the outcomes or more properly organized analysis into the reasons behind the outcomes. An architecture for data mining. Just outside of the warehouse, several data mining currently run, requiring extra steps to retrieve, import and analyze the data. Figure 1 demonstrates the advanced analysis architecture of a large data warehouse. An OLAP server makes to implement a more sophisticated end-user business model. To incorporate ROI-focused market analysis directly into this infrastructure, the data mining server must be integrated with the data warehouse and the OLAP server. Primary data mining tasks. 1. Classification discovery of a function of predictive learning G that categorizes a data item into one of many predefined G groups. 2. Regression discovery of a predictive learning function, which maps a data item to a prediction variable of real value. 3. Clustering is a common descriptive task in which a finite set of categories or clusters is defined in order to classify the data. 4. Summarization, an additional descriptive task requiring methods for a set, or subset, of data to find a compact description. 5. Dependency modeling, finding a local model that defines significant dependencies in a data set or in a part of a data set between variables or between values of a function. 6. Detection of shift and deviation, discovering the most relevant changes in the data collection. 3. Mining spatio-temporal topological relationship patterns. If the geometry or location of either of the spatial objects changes, the topological relationship between the two spatial objects can change. In general, the geometry and position changes of spatial objective are collected and stored in spatio-temporal databases over time. Using spatio-temporal topological relationship patterns, the evolving topological relationship between spatial objects and time is depicted. The topological relationship shifts between two spatial objects O1 and O2 from time t1 to t4, for example, is shown in Fig. 1. For this example, the topological relationship pattern can be expressed as DOCT, where DO, C, T, respectively, corresponds to disjoints, overlaps, contains, and touches. It is possible to compute support for such patterns so that it can be used in decision making. If these patterns occur more than the number of times stated, then they are known as periodic patterns. 4. Temporal data mining. Data warehouse containing a mixture of internal data monitoring all customer interactions, combined with external market data on competitor operation, is the perfect starting point. When accessing the data warehouse, the study of events ordered by one or more time dimensions is concerned with temporal data mining. In two broad directions, we distinguish. One concerns the exploration of causal associations between events that are temporally focused. The other concerns the discovery within the same time sequence or among different time sequences with similar patterns. This latter field focuses on the detection of similar pre-specified trends, generally called time series analysis, or trend analysis. 4.1 Mining temporal sequences. Temporal data mining's aim is to uncover secret connections between event sequences and subsequences. Three phases are mainly involved in the exploration of relationships between sequences of events: the representation and modeling of the data sequence in an acceptable form, the description of measures of similarity between sequences, and the application of models and representations to the actual problems of mining. A sequence consisting of a set of nominal symbols from a given alphabet is commonly referred to as a temporal sequence, and a sequence of continuous elements of real value is known as a time series. 4.1.1 Representation of temporal sequence. Time domain continuous representations. The initial elements, ordered by their moment of occurrence, without any pre-processing, are a simple approach to representing a sequence of real-valued elements, time series. An alternative involves finding a piecewise linear function C capable of representing the entire initial series roughly. The goal is to obtain a representation that can detect important changes in the sequence. 4.1.2 Transformation-based representations. The key idea of transformation-based representations is to transform the initial sequences from time to another domain and then to represent each original sequence by using a point t in this new domain. To transform a series from the time domain to a point in the frequency domain, one proposal uses the discrete Fourier transform, DFT. The discrete wavelet transform, DWT, uses a more recent method to convert each series from the time domain into the time/frequency domain. The DWT is a linear transformation that decomposes the original sequence into various components of frequency with OUT losing knowledge about the moment of the occurrence of the elements. 4.2 Temporal data mining tasks. In a broad number of applications, data mining has been used. It is possible to group temporary data mining tasks as follows. Focused market analysis. Directly focused market analysis. Directly. I. Estimation. 2. Classification. 3. Clustering. 4. Search and retrieval, and v. Discovery of patterns. The role of predicting time series has to do with estimating, typically, future time series values based on their past. Focused market analysis directly samples. One needs to construct a predictive model for the data in order to do this. 5. Spatial data mining. Objective. The key difference between data mining in relational DBS and spatial DBS is that the characteristics of the neighbors of an object of interest may affect the object and must therefore be considered. Implicit spatial neighborhood relations that are used by spatial data mining algorithms are defined by the explicit position and extension of spatial objects. Database primitives for mining spatial data. A collection of primitive mining database primitives in Spatial databases that are sufficient to express most spatial data mining algorithms and can be efficiently assisted by a DBMS. Efficient support of DBMS. Active filtrace allow the search to be restricted from a starting object to certain neighborhood paths leading away. To facilitate efficient retrieval of database primitives by a DBMS, neighborhood indices materialize certain neighborhood graphs. Softwares for spatial data mining. 1. Crimestat, a geographic statistics method for crime event analysis and its locations. Description: Crimestat is commonly used by crime research ERS and practitioners as a spatial statistics tool. The software is Windows-based, and most desktop GIS programmers interface with it. The goal is to provide additional statistical resources to assist law enforcement officials and researchers in the field of criminal justice in their attempts to map crime. 2. Toolbox for spatial statistics for Matlab/Fortran by Matlab and Fortran Toolbox for computing simultaneous and conditional spatial autoregressions and mixed regressive spatially autoregressive models developed by Pace, free software. Description: speed of the Louisiana State University Department of Finance. 3. Matlab Spatial Econometrics Library, free software. Description: it is a complete collection of expansion functions for spatial analysis, including autoregressive spatial modeling in particular. 4. Terra Sears Cluster Seer/Boundary Seer/Spacestat, commercial applications. Description: spatial clustering, spatial autocorrelation analysis, K-function, and classifications are provided by Terra Seer software. 6. Spatio-Temporal data mining. The concept of spatial data mining, spatio-temporal data mining, here refers to the extraction of implicit information, spatial and temporal relationships, or other patterns which are not specifically stored in spatio-temporal databases. Data mining strategies. Spatialization and temporalization. Spatio-temporal data mining is the confluences of many fields, including spatio-temporal databases, machine learning, statistics, spatial visualization, and the theory of information. First, at different levels, scales, spatial and temporal relationships exist among spatial entities. In geographic databases, spatial relationships, both metric, such as distance, and non-metric, such as topology, direct form etc. and temporal relationships, such as before or after, can be explicit or implied. Second, the intrinsic characteristics of spatio-temporal databases are spatial and temporal dependence and heterogeneity. Thirdly, the influence of scale in space and time is a complicated research problem in geographical analysis. The method of spatio-temporal data mining. The process of data mining typically consists of 3 stages or steps. 1. Pre-processing or preparation of information. 2. Modeling and validation, and 3. Post-processing or deployment. During the first step, according to some constraints imposed by some software, algorithms, or users, the data may need some cleaning and transformation. The second D stage consists of selecting or creating a model that better represents the actions of the application. Finally, the third stage consists of using the model to study the application behavior effectively, which was tested and validated in the SECO-ND process. The intrinsic feature of spatio-temporal databases is genetics. In a study of temporal information exploration, 4 broad categories of temporality within data are classified. Static, time has to be traced through external knowledge such as the creation of databases, sequences, ordered sequence of events, showing relationships like before and after, or the richer relationships defined as meeting, overlapping, contemporary, time-stamped, a static data-timed sequence taken at more or less frequent intervals, completely temporal, spatio-temporal data incorporated, via, for example, incidents, processes. Cascading spatio-temporal pattern discovery. The discovery of cascading spatio-temporal patterns from a Boolean data set of spatio-temporal event types uncovers partially ordered subsets of event types whose instances are located and serially occur together. The forms of spatio-temporal events and their cases are distinct. A cyclone is, for example, an event type. At various time, it can occur at several different places. Each instance of an event is correlated with a specific place and time of occurrence. If event instances have disjointed occurrence times, the ordering can be total ordering is, otherwise, partial. Analysis of climate science datasets to detect repeated occurrence of ice melting, extreme flooding with rainfall in some areas and drought in other areas after global warming are examples of CSTP. Discovery of cyclone incidents, heavy rainfall, strong winds, localized flooding, wind damage, and post. Spatio-temporal data mining system requirements and applications. Spatio-temporal database structure. Let the S be the space or geographic region for which spatio-temporal information is gathered. Suppose S contains regions R1, R2, Rn and each internal region. On contains spatial objects O1, O2, OK at T1. As time passes, various potential adjustments are made. 1. It can change the location of the regions. 2. One area can be divided into 2 or more regions. 3. In one country 2 or more regions can merge. 4. It can shrink or expand the area. 5. The objects can travel to some other area in one region. 6. The object's shape can shift. 7. The object's position within the area can shift. 8. About the combinations above. At regular and/or irregular intervals, the spatio-temporal database records the spatial objects and the changes happening to them over a period. System requirements. 1. The spatio-temporal data mining framework should provide the user with a GUI-based environment to specify different inputs related to the specific task data, the type of spatio-temporal task or information to be discovered, interesting measures and threshold values appropriate to the task, and to specify the visualization method of the knowledge discovered. 2. To produce the information effectively, the system should force down user inputs as deeply as possible into the data mining process. 3. Interactive review of data mining outcomes should be supported by the framework. 4. Research and development of scalable, computer-efficient data mining techniques is a major challenge. 7. Conclusion. Due to the widespread use of sensor networks and location-aware devices as well as domain-specific features associated with such complex data sets, the rapid growth of spatio-temporal datasets involves research into spatio-temporal data mining tasks. In different contexts, spatio-temporal data mining presents many problems and also E17 Diggle PJ, 1993, Point Process Modeling in Environmental Siting Applications. the research field remains largely unexplored. This paper explores the importance of the study and mining of spatiotemporal data in various fields, problems and challenges related to representation, processing, analysis, mining and visualization. It also presents the nature of spatiotemporal data, how complex it is and the need for scalable and effective algorithms. These massive spatiotemporal data sets also conceal attractive information and useful knowledge, perhaps. Many of the new services strive to provide consumers with more. It is evident that it is difficult to manually analyze such data and that data mining could provide useful tools and technology in this context. Spatiotemporal data mining is an increasing field of research dedicated to the development of new algorithms and analytical methods for the efficient analysis of large spatiotemporal databases.